Let's start today's class. It's about last class we learned about memory. Today we are going to learn about a new set of devices which is known as programmable logic devices. Okay. So what are the various types of programmable logic devices, right? So what are these devices? It is like it's an small kind of IC in which you can program for certain digital functions. It can implement certain digital combinational circuits, right? So it is not necessary that if you have certain inputs in an industry and you have various sensors and which can sense say the humidity, the temperature, or if there is a machine running, the RPM or the temperature of the oil system and all. So there could be n number of sensors, and the outputs could be driving a motor or stopping a motor or changing the speed of a motor and all. So these are the kind of functions which generally in day-to-day life in the industry we encounter. We need to design such circuits. So it is not prudent to keep a big microprocessor there or a PC everywhere. In many places a small ROM can be put or a small PLD can be put there. Okay, it is a very small component. It's a small IC on a small PCB. If we place there, it can essentially take a few inputs from the various sensors and provide the controls to the system. So so you understand what is a PLD. It's very it's not even a microcontroller, is also a big thing. Okay, it is even smaller than a microcontroller, like an Arduino. It can do several functions. Okay, this is even smaller than that. Even Arduino, we can put it's not prudent to place a microcontroller everywhere. Okay, these small PLDs can be part of the machine control itself. Suppose there is a machine, it receives output load, output voltage fluctuation, a lot of things it can sense, and we can do a small program and put it in the control panel of the machine itself. So these are all PLDs are you have an PC which can do large number of functions, and then you come down, you have an FPGA. If you come down again, you can have some microcontrollers, or if you still come down, you can have something known as PLDs. Okay, so it can sense a few inputs and provide some outputs. Okay, so that's the function of a PLD. So there are different types of PLDs available. One is known as a programmable logic array. Then there is something known as programmable array logic, PLA and PAL. Okay, something bigger than that is a simple programmable logic device. Okay, this does a little more functions than a PLA or a PAL. And then there is something known as complex programmable logic device. This can do much more functions than an SPLD. And then finally you have FPGAs, and which can do a fairly wide range of functions. Okay, so these are the various kind of PLDs. So the first two is going to be there in our syllabus. So I'll casually mention slightly about the next three. So the first two is part of our syllabus. These are just, you can skip this. You don't have to go into details of the last three kind of PLDs. Okay. So what is a PLA? Okay, PLA, programmable device capable of implementing functions expressed in sum of product form. So whenever a function is there in a sum of product form, so we can implement it within PLA. Okay, so all these input functions could be coming from various sensors, and the output could be some signals which could drive a relay, motor, and all things like that. Okay, so consists of input buffers and inverters. Then there is a programmable AND plane, and there is a programmable OR plane. Okay, can implement M logic functions of n variables. Limit is the number of product terms that can be generated inside the device. Okay, so this aspect will be clear when we see the block diagram. Okay, so this is the block diagram of an PLA. Okay, so this is power supply voltage. So this is the power supply voltage. This horizontal lines are all VDD, power supply, and the output functions are these F0, F1, F2, F3. Okay, these are the output functions. These are the input pins, input lines. Okay, A bar, B bar, C, and C bar. Okay, So this is the programmable, this left hand side is the programmable AND plane. Okay, so these are the programmable OR plane. Okay, the arrow which is pointing down from top to bottom here. So these set-offs. Okay, so how do these becomes an AND plane? Okay, so that, see, initially this is a V plus, that is the positive voltage is available on this line, right? If you give this connection out here like this, right? Okay, so then what happens is this line will be decided, the voltage at this line will be like, I will take this one particular case, this is VDD is available here, right? So you are putting an a diode here. Okay, this is a connection which is going to be made here. Okay, it is a fuse link between here and here. Once you make the fuse link, okay, what will be the voltage available here? Okay, it will be the, like, if it is A is equal to 0, it will be 0. If A is equal to 1, it will be 1. It will be available here, right? So this line, okay, essentially will be driven by A bar, right? Similarly, this vertical line, right? This vertical line. So if you see, if it is A, it will be driven by this fuse link will be here. So it will be A would be available here, right? So this is how all these horizontal lines, okay, and if you see why it is known as an AND plane. If you see, this is one line out here going here, right? If it is this is the second line which is coming here, right? There are two lines here. Okay, why are we calling it as an AND line? Okay, the AND line is when B is 1, right? Okay, suppose B bar, this particular line, since there are two lines are connected, it is known as A bar and B bar. Now we try to analyze why it is known as A bar and B bar, right? Because you are giving a VCC out here. Okay, when A bar is high, okay, so this is like a diode kind of thing, right? It is not going to transmit here, it's a fuse link. So this line will be high, okay, because it is high available here, right? So similarly, if this is also high, it is going to be high. In case any one of them goes low, okay, if any one of them goes low, so there will be a 0 here, right? So through this diode, okay, 0, this line will become 0. Even if this is 1, okay, if this is 0, this will become 0 out here, right? So that is why it is known as an AND gate. Is this aspect clear why it is an AND gate? Anybody has got a doubt? I can repeat this aspect.
So could you explain one more time, sir? Especially the part about the arrows.
Yeah. Okay. These arrows are kind of diode connections. Okay. So what happens is, if say A bar is high and B bar is high, okay, so if it is a high here, this voltage is available on this line, it will be high, it is available here. This is V plus, there is a resistance which is placed here, right? So it will be high. If one of them goes 0, say A goes 0 and B is high, right? So you have a V plus out here, you have a resistance here. So you will have a current flowing from V plus to A bar like this, if A bar is 0, right? So whatever is the V plus voltage which is available, that will get dropped across this resistance and you will have a 0 out here available here. If any one of them goes 0, okay, so the current will flow from the positive voltage what is given here through this resistance into the 0. 0 is a ground. So if any in this particular, in the first row, okay, in the first row, okay, you have a diode which is connected from the A bar towards A bar, from this V plus, from this horizontal line, a diode is connected here. From here, this diode is connected here. So if any one of them goes 0, a current will flow from V plus through this diode into that net. So the entire V plus voltage gets dropped across this resistance. Okay, so that is the reason why all these resistances are required in this particular cases, because otherwise V plus will get shorted to ground here. So the only way this line remains 1 is in this particular case, because if you see, this is connected to A bar, this is connected to B bar. So the only condition at which this line will remain high will be when A bar and B bar are high. Is this aspect clear? No problem. If it's not,
So aren't the NOT gates supposed to be single direction flow and the current can't flow in the opposite direction back towards A? Like if the current can't drop across it in the reverse direction?
no. If you have seen an CMOS gate, okay, all CMOS gates will be like a PMOS followed by a NMOS in the bottom. So it can sink current. There is no issue. It can draw current. There will be a ground there.
Okay, all right, sir. Thank you.
Okay. Should I flash and let me just see. Okay, you can see this figure. You can see this figure, right? This is
Yes,
how
sir.
an inverter, you give a positive voltage, this NMOS will be on, this will be off. Okay, so when NMOS is on, when this is off, whatever is charged here, what was stored here will get discharged, and this ground will be available here. So if through a resistor there is a voltage here, it will sink current. It can sink current to 0. This PMOS will be off, and this is high here. Okay, in a case high. So there will be an whenever we have, in our case, you have a resistor here and you are connecting it, so it will be able to sink current and pull it to 0. There is no issue with that. Is it okay?
Yes, sir.
Okay. So okay, I'll take one more example. Let's be very clear of this. See, for this particular line, okay, for this particular line, right, you have A being connected here, right, here, and you have this is the C bar line. So the C bar is also connected. So on this on the second horizontal line, it is connected to A through a diode, and it is also connected to C bar, right? So if these two, if they are not connected, for example, then you have the VDD voltage which is available here. Okay, that means on this horizontal line there will be a voltage +5 voltage. Okay, in TTL. For other, it will be whatever is the VDD. So say the 5 volt is available here, so it is a 1 here, right? But now I have connected one diode and put it here, and another diode, and I have connected it here. In this case, what happens is, if either A or C bar goes 0, this line will go 0, because a current will flow through this from the VDD through this resistor. So that 0 will get reflected here. So all the voltage will be dropped here, and whatever is the 0 which is coming from A or C. So essentially this line turns out to be A C bar. Is it clear to all of you? Yeah, Shriya, Siva, Shankar, is it clear?
Excuse me, sir.
Yeah, tell me.
Sir, at one point of time, we wouldn't be like giving a current across all the 5 V plus lines.
We will be giving the voltage here. This is not an SRAM. Okay, here all the VCC will be, this is not a ROM in which we are using a decoder. Okay, this is a PLA, and we will be giving this +5 voltage across all these resistances. Only the input combination would change.
So, sir, in that case, then, like, from if you just consider the first horizontal line,
Okay.
where we are giving V plus,
Okay.
if A goes to 0, then it will just short there itself, right? On the first intersection.
If A, here there is no, it is not connected, right? It is not connected here.
like if you just take the first line,
Okay.
whenever A goes to 0, then this would get shorted, right? I mean, all the current would flow into the ground.
No, okay. When the A goes 0, right? The second row will go to 0, right? Because there is a diode connected here, right?
Oh, okay. So those aren't okay.
Yeah,
Those aren't connected. Fine.
I'll just explain you that aspect. Okay, when the A goes low, okay, this is connected out here. Okay, assume I have put an 10k resistance here and it's a 10 volt. Okay, just for simplicity of calculation I am telling you. Okay, so if it is a 10k here, right, so what is the current which will flow into this is 10, it's a 0 out here. So 10k 10 volt divided by 10k, so 1 milliampere current will flow in this particular branch. It will come through this resistance, through this diode, it would go to A, right? Whereas these horizontal lines are not affected because you have a voltage here and there is a resistance here, but from this resistance, and suppose it won't go to A bar because A is 0, A bar is high, so it won't go to 0 there. So only currents will flow in those branches where there is a 0, wherever there is a 0. Is it okay?
Yes, I understood. So only where those black dots are, only those are the connection points.
Yeah, wherever these are the black points, they are the connection points.
All right, thank you.
Okay, so it is slightly different from the ROM what we studied. Okay, so this is known as the AND gate programming. So when we write a programming, so there will be certain fuses like this or the diodes. Okay, so they, as per our program, wherever we want, it will get programmed. So there will be softwares where we will define, okay, wherever we need these connections. Okay, so how these connections are made, so that we have studied in the last class. There are many methods of making these connections. So we saw in an EEPROM where we used a floating gate, where electrically we were able to program this connection and electrically we were able to erase these connections. So that's how we do the AND plane programming. Okay, now we can also do the OR gate programming. Now for an F0, if I want A dash B dash, okay, now I make these connections out here. So if it is, say, if it is 1 out here, so 1 will be reflected here, and this is an again a high resistance, okay, and it is put a ground here. If it is not a 1, okay, if it is not a 1, so this diode will remain, these diodes will become open, right, because it can only conduct current in. But to ensure that it is, if it is not a 1, to ensure that it remains 0, you put a high resistance and a ground here. So this will become a 0 in case these lines are, say for this particular condition, okay, these lines are not connected at all, only this line is particular connected. So whenever there is a 1 available on the last line, right, on the last horizontal line, F3 will go high, and whenever there is this F3 is 0 here, okay, diode cannot, if some charge is trapped here, this diode cannot pull back because it is only condensed. So in that case, we have a resistance and a ground here, it will go to 0. So this is how the OR plane programming is done. Okay, is it clear to all of you? If it is not clear, I can explain once again. Just it's a simple thing, but if it is better if you understand it properly. Is it okay?
Sir, so what exactly is the output representing here?
Here, yeah, can anybody guess what is F0? F0 is A dash B dash plus AC dash. If any of them is 1, here F0 will be high. Is it okay? Similarly, F1 will be A dash C dash, or what is this function which has come? It is only B is connected here. So or B. Is it okay?
Sir, I have a doubt.
Yeah, ask me.
Sir, aren't all of these fixed? I mean, the diodes and everything.
See, there will be diodes in each of these connections, okay, initially, right? So when we program it, either we erase those diodes, or we there are two methods. In EEPROM we see that we make these connections. Okay, there will be floating gates. So during the programming we make these connections. Okay, by putting a voltage there, and on the floating gate we put a charge. So these connection, once we program it, that charge will remain permanently there till we erase it again with an programming device. Otherwise, once this device is programmed, it will remain like that even if the power supply is gone. Okay, so that will remain like that till we again use a software and a proper tool to erase the data.
So how exactly is this PLA programmable? I didn't understand that.
See, see, there are these are the, if you see, let me go back to my previous in the last class, if you remember, okay, we had made these connections, right, using EEPROMs. Initially I told you there are masks, then I showed in the prompts there will be some fusible links whichever we don't want, we can blow them out, right. Initially there will be there are two prompts. Okay, if you have forgotten about that.
Oh yes sir, I remember.
You remember that, right? So these are also programmable links. Okay, these are two planes. Let me just try and get that files also, so that you just remember that. We discussed this, right? These are the two I don't know why the mouse is not coming on to that. Okay, these are the two kind of lines which are running. In between you see these fusible links, so these can be blown off, right? Similarly, when we saw the EEPROM, I said these are the EEPROMs where you have an these links. See that there are two vertical lines and the horizontal lines which are running out here, and each of them can be connected by giving a appropriate voltage during programming, so that they make permanent connections there. If you give a very high voltage, then some charges will be trapped on the floating gate. So there on those nodes, on those wherever the wires are running cross, okay, interconnections will be made, so that the charges will be trapped there, and subsequently we can erase that by giving a reverse voltage. Okay, so I hope that is clear. Is it clear how these connections are made?
Yes sir.
Yeah, that we last class. Okay, so
Sir,
yeah, tell me.
sir, I'm not able to understand this first diode between A bar and B. Like, what's the use of that? Yeah, no, sir. Yeah, this one. Yeah.
This one
Sir, no, not sir. In the AND side, on the AND side.
here.
Yeah, sir. This one only.
So see, this is the AND line. Okay, so now what are the minterms we want in this line? So this is just an example. Okay, these functions are just showing an example. Okay,
Sir, I'm asking like, where is this connected with? Like, all these lines are running parallelly, right? So what all things are connected?
see, these are first of all, this is not universal. This is just an example of one particular function where F0 is defined by A bar, B bar and A C bar in this particular example. Okay, so this is a snapshot of not an full circuit. It is programmed for some, it is already programmed for a specific function. Okay, now this particular horizontal line is known as the AND plane. Okay, so this will see, it is connected to plus V voltage here, and a resistor is connected here. So ideally, if you don't do anything with this line, a plus 5 voltage will be available here. That means a logical 1 will be available on this particular and line. Okay, or you can, this is an AND line, this entire becomes a, on this AND line always there will be plus 5 voltage. Now for certain conditions I don't want plus 1 to be available here. Okay, so for what are those conditions? Now if you see, these diodes will define those conditions. This is put here as A bar and this is put as B bar here. That means whenever either A bar or B bar, one of them goes to 0, this particular line will have a path to 0, okay, through these diodes. If there is a path to 0, the current will flow from this V plus through this resistance to 0, and this line will be forced to 0. So essentially this line now can be called as A dash B bar, A bar B bar line. Is it okay?
Yes, I got it.
Okay, so this is an this is actually, by connecting these two lines we have implemented an AND function. Okay, so this AND function is A bar B bar AND function. Okay, so this is just an example of these functions. Okay, so similarly this particular line is connected to A and also it is connected to C bar. So this particular line can be called as A C bar. That means this line will be high only when A and C bar both are high. Now if you see this vertical line, this is now the OR plane. These are known as the OR plane. This is the AND plane. This is the AND plane where you have AND horizontal lines. This is the OR plane where we have the OR vertical lines. Now these are connected again through diodes out here. So if A bar, either A bar B bar is high or A bar C bar is high, this line will become high now. Okay, it will become high because a voltage will be applied here, right? But although it is connected to the ground through a resistance, so that high will not disappear. Only thing is some current will flow in this path. Okay, so whenever, if both, for a situation where both are zeros out here, so these diodes will not be there. So just to ensure, if no connection means it has to be 0 actually, right? So we have put a resistance at the ground, so it will be ground. Effectively there is a connection to the ground here. So is this OR plane thing clear to all of you?
Yes, sir.
Okay, so let me
So just a doubt, like
yeah.
I just wanted to confirm here, like F2 we will say that it's A dash B dash plus BC dash.
Yeah, correct.
Okay, so F3 will be B plus AC, like that only.
Yeah, correct.
Okay, got
Okay.
it.
Now can somebody tell me what is the use of these resistances? Is it required?
So is it to absorb any sort of heat?
No, it is required because see
Sir,
this line has to go 1. When this is high, it has to go, this line has to become 1, right? We can't connect a ground directly here. If you connect a ground here, if you put, when A dash B dash goes high, voltage 5 volt will come here, that will get grounded, it will get shorted. So you have to put a resistance here. Then why at all to put a resistance here? Then the next question should be, okay, can we just keep it hanging so that if there is a 1 it will get connected here, if there is a 1 it will get connected here. So in that case, what happens if there is, if this is 0 and this is 0, right? This may not go to 0 because these diodes will get off. Okay, they cannot conduct back. So say for a previous condition there it was a 1 out here, now the inputs have changed, now it has to be a 0. So whatever charge has got, stray charge has got accumulated on this line, that cannot go back, flow back in these diodes. Okay, so they need to be discharged. So you put a resistance here. So this resistance will ensure that to a ground, this ground connection will ensure that whatever charge was accumulated in the previous state because of these lines being high, they will find a path to ground here. So this will act like a perfect OR. Okay, so only when there is any one of them is high, it will high will come here. Okay, and some current will flow in this resistance, doesn't matter. Okay, because it will not cause any voltage, because voltage is coming from here like this, so it will continue to remain high. Is this aspect clear to all of you?
Sir, so how will we change the diodes then in case we want to change the output?
No, I told you PLAs are, once you program it, it will give you, say for, suppose this is temperature, okay, and now this is an oil pressure, okay, this is the say on off switch input, okay, this is the mode of operation, okay, say 3 different inputs are there for a machine. Okay, now you are programming initially, okay, if the oil pressure is low, and say that the temperature is high and the on off switch is there, then you switch on, say, the oil pump, okay, so that is programmed initially. Similarly, you have these 3 inputs here, you are saying, see, if the oil pressure is low but the switch is off, okay, then even if the oil pressure is low, you should not switch on, because the switch is off, it should not switch on the pump. So certain conditions, real life conditions, already it is fixed here. These are the inputs coming from the sensors, these are the outputs. So essentially we know, okay, how it is to be programmed, and then once it is programmed, and then you just connect the inputs and the outputs, right? You don't have, there is no dynamic changing of the functionality here. Is it okay?
Yes, sir.
Excuse me, sir.
Yeah, tell me.
So, like, we are collecting only 2 minterms on each output. So, like for F0, we are collecting A dash B dash plus AC dash. We could have also collected all of them on F0 itself, right?
Correct. So that is as per the program. Okay.
Okay, sir.
Okay,
Understood.
that is how we define F0, F1, F2, F3. So depending on that, you can collect, and you can collect all the 4 minterms also, or all 8 midterms also, so that will be there, right? Is it okay?
Yes, sir. Understood, sir.
Okay.
Thank you, sir.
But many PLAs which come in the market, okay, they will have an restriction of number of OR lines you can connect here, okay, like total you can have 8 lines out here, right, in the AND plane. In the AND plane, can we have 8 lines, 8 different lines, horizontal lines? No, these are vertical lines. Okay, there will be in this case there are 6. You can have n number of horizontal lines, but the number of AND lines and number of the OR lines, okay, will generally be restricted in a PLA. It may not be infinite, right? They will specify you can how many number of terms you can connect. So accordingly, you will have to choose the PLA which you want.
So the maximum number of AND lines will be just 2 to the power of number of inputs, right? Like in this case, we can't have more than 8 AND lines. We won't need them for any type of circuit.
Correct. So generally, all the 8 AND lines will be available, but OR lines, they will be specified. Each PLA by a different company, it will have a number of output lines will be like 4, 8, 16. So you will have to accordingly select the PLA. Okay, there will be series. Say Texas Instruments will have a PLA, and say it will specify the number of outputs. So accordingly, for a particular application, you will choose depending on the how many number of outputs you require. You will choose the PLA that way. Is it okay?
Yes, sir.
Okay. So this is one example. Okay. So where we have to implement this function. So this function. So this is how we are going to represent this function here. Like somebody had a question whether we can connect 3 lines to a function. It is possible. In this case, 3 lines have been connected. See, if you see 3 OR planes. So this is how the representation is there, right? So from exam point of view, this is what is expected out of you. If they say okay, so this will be like 352 PLA. So the PLAs will be specifications will be like this. 352 means okay, there are 3 inputs, 5 AND lines and 2 OR lines. So if you see the technical specifications of PLAs, it will be given like this 352 or 383. So depending on the application, we can choose one of those PLAs. Okay, and there will be very user friendly softwares to program it. Okay, you don't have to really do all these things. There will be some metrics kind of thing which you will have to fill, like you filled the ROM metrics. So we are not going to learn about what programming language for each of these PLAs, because each PLA will have their own small code and a software which will give simple instructions. There will be, you can just pull the PLAs, do the interconnections and write some functions there. There will be options. So each company has its own kind of small program. So, and it is fairly simple to program it. Okay, so these kind of small PLAs in wherever, say in a washing machine, right, you could use a small PLA. Okay, what are the sensors? You have that lid close and open, right? So if you have a lid, say the spinner has to rotate. Okay, what are the conditions? One, that lid has to be close or open. Second condition could be that your drain is off. The third condition could be like there is a counter, right? If you have set it for 15 minutes, it will count for 15 minutes and then it has to stop. So there are 3 variables. So for a simple washing machine, there are these 3-4 conditions are available. So you, instead of using an FPGA and all, those kind of machines will have a small PLA. Similarly for your fridge, right? There could be 3 or 4 conditions where there is a temperature sensor, there could be a humidity sensor, and these modern day fridges, they have that quick cool. So if you press that, the compressor will run continuously at a faster rate. So all those conditions. So many places where some simple for your AC, for your ACs, or for your fire sensing and distinguishing system, what you have in our. So you don't require a complex FPGA or an PC to control such, where we know, okay, it's not dynamic. Once you program, it will remain like that for years together. You don't have to dynamically on a day-to-day basis change things. So many, there are n number of applications like that. Okay, so we can do that. So this is, and the programming is pretty simple. For each PLA, there will be a small kit. You can put it on that and you can program it accordingly. Okay, so now if a question is given like this, can you draw these kind of circuits? If only, say if I give some F1 min terms, F2 min terms, and ask you to implement a PLA, will you be able to draw this circuit? Anybody has got a doubt on how to draw this circuit from min terms if a min term is given? Say if I give F1 is equal to 0135 and ask you to implement a PLA, so this is how you are going to implement it. Okay. Okay. So let me move forward from here.
So just a doubt, just to clarify, the horizontal lines on the left side, they are connected to voltage sources, right?
They are connected to voltage sources. Yeah.
Are all of those like 5? We are giving 5 volt?
No, that depends on the family. It is okay. CMOS family will have 5 volt. TTL family will have. CMOS family can have other voltage. TTL family will definitely have 5 volt.
Okay.
Right. So it depends on the family. Logic 1, logic 0. Right. Okay. So now we have something known as a slightly different one, which is known as we first saw programmable logic array. Now we are going to see programmable array logic. Okay, here we can't program the OR plane. Okay, only the AND plane is programmable. This is already hardwired, the OR plane. So excuse me, so the disadvantage is that it is not as flexible as PLA. You can only program the AND gate, but it certainly reduces the hardware. The chip will become very, very small, because if you see all these AND gates also, again you will have to have fusible links here. At each of these links, okay, there will be a floating gate MOS transistor switch, okay, which can be programmed here in a PLA. So for each of these junction 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more MOS transistors will be required, which can be programmed for these connections. So in an PAL, okay, they are already hardwired, so there is no way you can program that. So it will become compact because those MOS transistors are not there. So it will be like programmed here. Like
excuse me, sir.
Yeah, tell me.
So in PLA, the number of OR lines we had were basically the number of outputs, right?
Yeah, correct.
So even in PLA, the number of OR lines were fixed because we have a fixed number of outputs.
No, even for these two lines, we could program each of these OR lines can be programmed to which AND gates they are connected here. Okay, now I can connect F1 to the either to 2 gates or 3 gates or 4 gates. That flexibility is available in my design here, okay, in a PLA. Whereas in a PAL, if you see here, okay, this is already fixed to this F1 is already fixed to these two AND lines, and this F2 is already fixed to these AND lines. Okay, so there is no flexibility in design here in the PAL. Is it okay?
Yes, sir, got it.
Okay, so there is no flexibility here. Okay, this F1 is OR of this line and this line. Now what we want here, okay, what are the functions which we want here, that we can program, not necessarily 2. Here it is we can have an 3 AND also. Okay, here it is shown 2 to 2. Okay, we can have 3 AND also, right? X1 is connected here, X2 is connected here, you could connect X3 also. That is not a problem. There is a flexibility in this plane, whereas in this plane there is no flexibility. Okay, this makes this slightly compact, so that in certain applications it is used. Is it okay how a PAL is programmed? Is it okay with all of you? Yeah, okay. So there could be some questions in PAL based also. Some min terms will be given here. So how do you? So you just have to put crosses at the appropriate places. Okay, that's all. Okay. So for both PAL and PLA questions, okay, for the exam point of view, you need to just find out the appropriate place where you need to put the cross. Okay, so in the net you will find numerous examples of PL and PAL, and in the I have put few examples in the tutorial also. In Tuesday's tutorial we will discuss a few more. I'll put the questions early itself so that you can do a practice of that. So all that for the exam point of view, you need to know how to put the crosses. Okay, and for the practical application point of view, you need to know that okay, these are fixed and this is available like this. So if a PAL is already given to you, you should know how to program it. Okay, so they are not very difficult. Just keep these things in the background of your mind. So there is no point getting very deep into the programming and all, because they are only half an hour thing, which when you actually start implementing something in a factory, we will do that. Okay, FPGA programming, obviously you will do it in your next semester, so you will become confident of that. Okay, so some of the PAL ICs have an feedback from the first output also. Okay, so if you see, this is one of those practical PALs which are available in the market. If you see, this W and W bar is available as these two AND lines out here. Okay, could you see the difference? What is there? If you see this line, okay, so this additional things is available here, these two lines. Okay, what it does is, suppose one function which is common, okay, in the first function when you are implementing, if you find W which can be used in X, Y and Z, so that is also available as an input line available here. So in many cases, some function, okay, is used repeatedly for the other function. So this PAL provides this feedback here. So we can use these lines as an inputs for these AND gates. Is it okay with everybody? Am I online, or I have gone?
Is it similar to a flip-flop where we can take the output and put it and put it back as an input
No, this is an
for W?
no, this is it doesn't wait for any combinational circuit. Suppose I'll give you an example of this, then it will be clear. Okay, suppose we are programming W as say ABC AND of ABC. Okay, for example, I am giving, and now I find that the minterms of these also contains ABC. In that case, okay, I don't have to again program for ABC here. I can, this function which is already available in this line can be used here. Okay, because in this PAL it has got only 3 AND gates, right? Okay, now suppose this requires 4 AND gates, and the 4th AND gate is ABC, which I have already implemented in the first state. So I will be able to take that and use it for in these implementations. Is it clear? I think we'll see an example.
Sir, so
yeah.
So we could like use this to get past the limitation of total number of inputs that we have, as we discussed previously, that if we have say a PLA that can take only 3 inputs at a time, so we could like use this. If we have a expression which has say 8 variables, then we could combine PLAs like we could accordingly split terms and get the minterms out of each PLA.
Yeah, correct. So we can use that aspect. We can do that. It will be very clear once we see an example. Okay, how? Say W is this. Okay, there is a function which is a minterm which is given. X is this, Y is this, and now there are 3 functions which is required to be implemented. Now first of all we need to expand it, right? Okay, so we need to know W, X and Y. So these are the functions. Okay, A, B, C dash, right? So now so if you see this third one, Y, right, these functions are already implemented in W, so I can write it as W out here. This has got 1, 2, 3, 4 AND gates it requires, but this has already been implemented by W, so you can write it as a W, and then these two. Okay, is this aspect clear? Then we'll see the implementation part. Is this clear? We have just, there are 3 functions which it requires to be implemented. The minterms have given, so we have written down the expressions. Okay, once we have written down the expressions, right, we find that this is common. This is W is already implemented here, so I put a W out here, and then I put the rest of the thing. And in the implementation part, when we see, right, so we write it like this. Okay, this is W, right? This is the AND plane, A, B, C dash. So right, and A, B and C dash, D dash, D dash, we are putting a dash here. Okay, because in the AND plane, wherever there is a 1, we are going to make a cross there, right? And for 0 also we need to make a cross with C bar. Dash means we are going to leave it as it is. We are not going to make any connection. Okay, so don't make a mistake in the exam of putting only cross where 1 is there. Okay, wherever there is a 0, you need to make a cross with C bar. Is this aspect clear to all of you? Okay, so this is W, right? For the next expression, we are writing an A bar, B bar, C and D bar. Okay, so let's see the diagram and we'll come back to this later. So if you see here it said in this it's put a cross out here, and C bar also a cross is been put here. Can you see the cross? If it is not very clear, once I share the PDF, you will be able to see. Okay, so there is a C bar cross also put here. So this is, it requires one more AND gate. Okay, so that in the second expression, if you see, it is 0 0 and then 1 and 0, right? So if I go 0 0, so the bar lines have been put, and then 1 is put here, again bar line is put. And for the third AND gate, okay, nothing is put. If nothing is available here, so it will assume, okay, there is an 0 available here, so there is no connections made here. So this is going to be 0 here. right? So these are the connections what we are going to make here, like these connections, right? So similar. Now if you see for the last expression where we are going to use, so this W which is available here, we are making another 2 vertical lines which is available here for the first function. In the PLA, generally one function output is available here. So if it is available here, for the last one, if I go back, for the last one I am going to use W also. So this is W is going to be 1 here. So that W we are going to use it here for this particular AND gate. That W has been put here. So there is a cross available here. So is it okay? How this?
So one small doubt, sir.
Yeah, tell me.
So here basically W is used to simplify the expression because we have repeated terms, right?
Correct.
So if we have a lot of variables and a lot of outputs, then some terms will definitely be repeated. But then how will we know how many terms are repeated, and how will that be programmed? And
yeah. So if it is going to be a large type of variables and there is lot of interconnection, then obviously PAL or PLA is not the solution. Okay, these are all for simple logic applications. Okay, I told you the applications like for a control of a motor, control of even a lift requires lot of inputs. If you see, there is a speed control, so we generally don't use we use an microcontroller for a lift. For simple applications like a washing machine, fridge, your AC, so such simple applications only we use this, right? So and each PAL will specify, okay, the number. There won't be 10 or 15 outputs available. It will be maximum 3, 4. This is one of the largest PLAs which you have. Let me go here. It has got around 4 outputs and then 4 sets of inputs and 1 feedback. Okay, is it clear? Is it okay? This is manual.
Yes, sir.
Okay, and these things we need to do it manually only, understanding the limitations of the PAL. Okay, so we go for the highest PAL which is available in the market. Okay, we know the interconnections here, then manually we have to decide, okay, if there is a common we can use that. So there is no rule like K-map or for simplification of PAL logic. It is all manual. These are all what 10% of what your CPU can do, or maybe even lesser, but it will save your energy. This will require just a small voltage supply, and it can be integrated easily onto your small machines. So that is the application of these PALs. Is it okay, all of you?
yes, sir.
Okay, so these are the 2 things which are there in the syllabus. So I think the questions will be very straightforward, and you should know where to put the crosses. That's all. Okay, so I will upload the tutorial also, only the questions today itself, so that seeing the questions and then you can just search the net for some of the applications. Anyway, solutions will be given to you on Tuesday, but in these 3-4 days you can try out some small problems regarding PLA and PAL which will be there in the exam. Okay, now okay, these are just so okay, you can see now the connections which have been made, right? Okay, these crosses are now visible. So okay, there is something known as PLA Spld. Okay, this is very rarely used, in which you have a provision to save the previous data also. Okay, so you have an like it stores data. Here there is no memory. Okay, whatever is the current input, the output will reflect that straight away in PAL. Whereas in Spld it can store a previous data also. Okay, so and there is a multiplexer. So this is just for the sake of completion of the flow, I have put this slide here. So just remember, okay, what is an Spld? It's just a PAL or PLA along with a memory element also. Okay, but this is very rarely used. Okay, here you see that the q and q bar is also available, because you have an flip flop here. So the previous states are also available for the AND plane. So that is what it does. And then you have something known as a complex programmable logic device. Okay, so in the complex, they are all different pairs, and it is not an AND and OR. Okay, so all these blocks can be interconnected with an IO blocks, and these IO blocks we can program. Okay, how to interconnect these blocks. So a wide variety of functions can be implemented using an CPLD. Basically, CPLD becomes an building block of an FPGA. This is an FPGA where there are small logic blocks. Each of these blocks can do a wide variety of functions. Okay, it has got memory element also in it. And then there are several IO blocks. IO blocks are input lines. Okay, you can give various digital inputs to these through these IO blocks. Okay, various inputs. Okay, for an typical FPGA, maybe 32 different input lines can be given. Similarly, there are some 32 odd output lines which are available. So when we write an Verilog code for FPGA, so we will define that input 1, input 2, input 3, input 4. We define those, and we also define the outputs, right? So when we write a code, what happens is we have not done FPGA programming, unfortunately, but once we write a Verilog code, we will define inputs and outputs, and then when we do the synthesis, it will make these interconnections. Okay, each of these logic blocks, if you see the RTL schematic, right, which we did in Xilinx, it will program each of these blocks to do those specific functions as per the RTL schematic. You don't have to do anything, the program will take care of that. It will use these logic blocks to implement the required function. Right, we just write what are the inputs, what are the outputs, and how they are related. So the program will be written in Xilinx, and once we do the Xilinx operations and we load that program onto the FPGA, so the interconnections will automatically be made here. All of you have seen that RTL schematic, right? Yes or no? How
in the Xilinx, sir?
In the Xilinx, when we
Yes, sir.
write a code, so that software will automatically use these blocks to implement that. Okay, and also these are all small interconnections. So the Xilinx will also program these interconnections, are also programmable, right? So like if this particular block is it's going to make it as a one module, you have made it as an D flip flop. Okay, the other one could be an AND. So these needs to be interconnected also, right? If suppose so all these interconnections will be programmed. So you don't have to do anything. It is not, you just write a code in the Verilog, it will program this FPGA, right? So till now we have learned how to program in Verilog in Xilinx. Okay, the next step what could have been done is,
So one small doubt, just to confirm, each logic block here basically represents a fixed number of inputs and a fixed number of outputs.
correct.
So it does different functions basically.
Yeah, it can be programmed actually. It will each block is a block like this. Okay, it's a whole block like this. It will have some inputs and it will have some outputs. This is an block. Within the block also, because each block can be programmed for a wide variety of function. Like suppose for example, it is a 4 inputs are there and 4 outputs are there. Okay, you can program is a 4 input NAND gate, or you could also use it as an you can program this block for that small block to behave like an adder, or a so wherein 4 inputs are there and 4 outputs are there. So so they are all complex blocks, each of them, and when we write in code, it will automatically use these. So we are not using this logic block. Each of this logic block can do a wide variety of specified functions. It can do addition, multiplication, few things it can do, right? and then we program it accordingly. So the program which runs when we do synthesis, it will make these it will program each of these logic blocks accordingly, and you program these interconnections also. Is it okay?
Yes, sir.
Okay. So when we do the program in an FPGA kit, right, we do the Xilinx program, and before we dump the program into the FPGA, okay, we will also specify, like this FPGA kit will have 16 pins, right? So when I say input A, there is something known as floor planning, in which I specify, okay, input A is pin number 1, input B is pin number 2, input output will be from pin number 16. So that kind of intermediate, there is something known as floor planning, which we did not learn in the lab because we don't have you don't have access to FPGA, right? So that is why I skipped that portion. So but you have learned FPGA programming 80%, I should say, okay, because it is basically Xilinx programming only. Now after the programming, how it is dumped into an hardware, so there is two steps in between where we do the floor planning. We just specify the pin numbers. The program automatically assigns the path, and also we don't have to do much about it. So that part maybe I'm not sure, because next semester is also going to be online. As and when you come back, okay, maybe I can organize a 1-day or 2-day workshop and give you some hands-on experience on FPGA programming. Okay. So don't worry about exam point of view. I'm just discussing this for your knowledge sake. Okay, is it okay? So from exam point of view, PAL and PLA you should know. Okay, so that is how an FPGA programming. Okay.
What is the actual size of the FPGAs in real life?
FPGA, is it? This particular chip will be only say 5 centimeters to 5 centimeters, but there will be lot of associated things. There will be a clock generator, okay, there will be some bus controller. So it will become a slightly big PCB, which is say a laptop monitor kind of thing. Okay, there will be one crystal, a few things, there will be some power supply regulators and things like that. So it's slightly bulky than a PLA. PLA and PAL is a small chip, whereas this is a PCB. It requires a small PCB.
Sir, and each logic block, how big will those be?
They will be nanoscale. They are all CMOS these days. So once I say an FPGA is an 3 inch by 3 inch or maximum 4 inch by 4 inch, okay, then inside that there will be millions of transistors. Okay, so these logic blocks will be in nanoscale dimensions. Is it okay? Shall I move it?
Yes, sir.
Okay. So this is the last slide for today. This is again not part of our syllabus, but I'm just covering it here. Right, till now we learnt about in the computer, when we say we have a ROM. Okay, generally we are not bothered about what ROM is there in the computer, right? Because that contains information of the hardware of the operating system and the motherboard. Initially when we boot up, whatever is the boot sequence and all is programmed in the ROM. Okay, that is done by the manufacturer. But I said then there is a hard disk, and in between we say there is something known as RAM. Okay, we are all bothered about the RAMs. Okay, if the RAM is big, then it obviously can bring larger portion from your hard disk into a temporary memory, which is known as SRAM, to run the program currently being executed. So that is the importance of SRAM. So how is an SRAM implemented is, if you have two inverters connected back to back like this, okay, so it will store that information as long as the power supply is there, because this inverter is going to drive this. Suppose it is a 1 here, it is 0 here, that 0 will be 1 here. So they form a loop here, and it will continuously that data will be available here. So whenever we want to write an data into this ROM, you close this switch. So whatever is the bit information which is available, that comes here. Suppose you're putting a 1 here, so that it will become 0 here, it is 1 here. Then you open the switch, then that information will be stored here itself. It will be, similarly, if you want to put a 0, you close the switch and put a 0 here. So 0 will make it 1 here, 1 will make it, and then you open the switch, again that information will be available here. So whenever you write whenever you want to read back that information, again you close the switch and you read this information from the same place. Okay. So this is how an RAM is. So all your RAMs are made up of such topologies. This is a very standard cell. So these two inverters, if you see, they are implemented with CMOS and interconnected like this. Okay. So there is 6 transistor ROMs here, and this is how we read the data. So this is a switch again. So if you switch it on, this data will be this is the same thing which is shown here, implemented with CMOS. Okay, so these are the so these are all the earlier version, it was all SRAM. Now you have DDR RAM and things like that, dynamic RAMs, which are much faster than this. It uses a lesser number of transistors. Okay, for you to understand how those RAMs, you have to have finished your microelectronics course. Okay, and probably it might be covered in ADVD. So just for your information, I have put this slide so that we know that. Okay, till now we are all talking about ROMs and PLDs. So there is something which is known as SRAM, and in SRAM also there is various. Now we are DDR. I think DDR3 and DDR3 is being used in most of the computers. So they are all temporary storage elements. Okay, so where we store the data and we retrieve the data. So that is not part of the syllabus, because the understanding involves basics about the transistor operation. So we are going to not study the details about that. Okay, so with that we finish this aspect, and then